So chapter 14 and 15 are both on my chapter 14, 15. Let me see what, I should put it up there for reference you guys in brown. 16 and 17.1-17.3. Round 16 and 17.1 to 17.3 are the materials that be covered in your book. Okay. So, acids and bases. We're going to start with the basics here. The earliest definition that was of any use for acids and bases, by the way, acids, strong acids and bases have been known for centuries. They were pretty well developed in the Middle Ages by alchemists. And most of our mineral acids we now have were developed then, such as hydrochloric acid, nitric acid, sulfuric acid, and there were a couple others. But the alchemists learned how to make those, purify them, and they were very useful in dissolving compounds and metals and ores and whatever else they were working with. But the first, what we would call scientific definition of acids and bases was proposed by a chemist named Arrhenius. He did a bunch of other stuff too, and his name will pop up again later. But Arrhenius' definition of an acid was any molecule that could release a hydrogen ion into aqueous solution. So that's my generic acid. You got the hydrogen and then everything else. And when we put it in solution, we get the separate ions, right? They're aqueous. And Arrhenius' definition of a base was there's everything else, and it had to have a hydroxyl in the molecule itself, so that when we put it in solution, we get that plus that. Right? And for most acids and bases, that's a useful definition. It still works for most. But the characteristics of the acid and the base were also known, and they discovered that there were certain types of compounds, when you put them in solution, they produce these basic, primarily the bases, basic solution. So independently, two other scientists, Bronsted and Lowry, proposed a different model. And what they said was an acid is actually a proton donor. So it doesn't just dissociate into proton and the rest of the molecule. There's actually a transfer of a proton in the process. So in this case, that can donate a proton. Well, where does it donate it to? If you put it in aqueous solution, the only place that it can donate is to a water molecule. So it donates that protein to the water molecule. Now the water molecule has a plus charge because the hydrogen is a plus, and then you have left over the rest of it. So this is an acid, a proton donor. Well, if we use the the flip side of that one, we say that the base is a proton acceptor. So in this model, water would be a base. It accepts the proton. But I've got another example of a base that does not have a hydroxyl in its makeup. And Bronsted and Lauer's definition explains why it's still a basic solution, but the molecule doesn't have a hydroxyl in it. And that's ammonia. When we put ammonia in solution, it does not transfer a proton from ammonia, it accepts a proton from the water. So now that the water is the proton donor, it's an acid this time, and that's the base. So what we have over here on the product side is this ion, which has accepted a proton from water, and what's left over is the hydroxyl. So that is why this is a basic solution, because of this reaction. And Bronsted and Lauer's model, it has much more extensive application than Arrhenius does. All right, so I spent a lot of time on that slide because I thought the basics, this understanding the basics was so important. I shot another 10 minutes out of our lecture. Okay, so this slide is just a rehash, really, of what I've done here, except that it also identifies this as the acid and this as the base. In this case, the water is the acid and ammonia is the base. Okay. Okay, this is just some animation. So it's like there's a tug of war between water molecule on the right with the red oxygen, and the blue ball is the nitrogen. And there's a tug of war going on between them on that proton. I was thinking, I think there's more that needs to be said here, but I don't have the animation for it. Okay. Let me, give me just a second. I'm going to get my hard copies. Okay. I'm going to talk about pure water in just a minute. I think that the statement by the B references something that I want to wait just a minute to talk about. Okay, so let's go to the next slide. Well, there is an animation for it. All right, I'll say this much. In pure water, two water molecules can approach one another, and there's also a tug of war between the two water molecules for a hydrogen. Right? I'll say more about that in just a minute. But by way of definition, when we have an acid and a base, or acid in solution, yeah, this works. So if we have the acid here, in this case, this is the proton donor, and this is the proton acceptor. So it's the base. And there's an equilibrium set up there, of course. So when we transfer a proton to the water, what we get is actually a conjugate acid. And what's left over from the acid on this side now is a conjugate base. Simply because it can now accept a proton. right? It would love to have, well, not necessarily. It depends on the acid. But it could accept another proton and go back the other direction from here. So in this respect, that's an acid and that's a base. It could go back this way. Okay. The chemical definition for strong versus weak. A strong acid is one which is essentially all one direction. If there's any return, it's very small. So strong acid refers to the degree of dissociation. All right, so if it goes mostly to the right, and then just a little bit back, then we say that's a strong acid. It makes no reference to the concentration, just the behavior of the individual molecules. Okay, now if this is a strong acid, then think of it as wanting to get rid of that proton. It really wants to lose the proton to get to the other side. Well, once you get to the other side, how do we characterize the conjugate base? Well, the conjugate base doesn't want that proton. They just got rid of it from there. So now we have, if this is a strong acid, that makes a weak conjugate base. Okay, because it does not want to accept the proton. That's what bases do. So this base doesn't want to accept a proton if it came from a strong acid. And vice versa, if this acid prefers to be complete like that, and let's see, it's mostly this way, but just a little bit that way, then it prefers to be here. That makes this a weak acid. It does not dissociate easily. That means that the conjugate base is a strong conjugate base. Because if it really wants to be here, this is ready and raring to go to accept a proton from somewhere. Okay, that's chemical definition of strong versus weak. And this is I'm not going to spend any time here. This doesn't help that much. Okay, so when we write this expression, let me remove some of the clutter. We can also write a K value for this equilibrium. So we're not saying whether it's strong or weak now. It's just an equilibrium set up between this, these reactants and these products. We can write a K and we'll subscript it with an A. This is the acid dissociation constant. It's an equilibrium constant, right? We use the same setup as before. We have products in the numerator. Like that. And notice this type of equation, all the coefficients are 1, 1, and 1, and 1 in this case. So that's why there's only a 1 up here as an exponent. And then the reactants go in the denominator. And notice this is a pure liquid, so it's not there. Right? In aqueous solution, the water is not there. Right? Pure liquids and solids are not part of the equilibrium, just like they were in the last chapter. But that would be an expression for the acid dissociation constant. Now, sometimes you'll see it, you'll also see it like this. What they've done is just remove the water from both sides. Take a water away from here, it's nothing. Take a water away from here, you're left with a hydrogen ion. Now, this is for convenience. This is not really the chemistry that's happening. The chemistry that's happening is a transfer of a proton from here to here. What we've discovered is that protons never exist as separate units in aqueous solution. They're always associated with something. But for convenience sake, the math still works for either one, exactly the same. And later on, this is going to be a useful expression when we get to it. I'll call your attention when we're there. So that means if this is very large, we have mostly product. And that means strong acid or stronger acid. When this is very small, that means this is small and this is large. And that means we have a weak acid. Okay. This property of water also occurs with some other compounds like ammonia, where in the pure substance, if we have pure water, then two water molecules can approach one another, and one of them can play the role of the acid and donate a proton, and the other one play the role of the base and accept the proton. And then you end up with a hydronium ion and a hydroxyl. Okay. This is autoionization, or another word for it is it's on the tip of my tongue. Amphoteric behavior. Ampho means both. So water molecule can behave as an acid or as a base, depending on the circumstances. So when these two approach one another, we can set up an equilibrium that produces a hydronium plus a hydroxyl. Okay? And we can write a K expression for this one. And in fact, we use a special subscript which is only used for this reaction, Kw. And that would be what goes down here? Nothing. These are both pure liquids. All right, so it's just that, hydronium times hydroxyl. And we also have a value. At 25 degrees C, this is 1.0 times 10 to the minus 14. So this reaction is mostly this way. Just very little of it is over here. But in aqueous solutions of any kind, no matter what you put in them, this reaction is always there and happening. It just depends on the reaction the other reactions that are happening at the same time. Are they going to have more influence on the hydrogen ion concentration in the solution than this one does? And the bottom example is ammonia. The same kind of thing happens there. You can get the ammonium complex ion, polyatomic ion, and then you can get the amine, NH2 minus. The amine molecule is the base for that reaction, and the ammonium is the conjugate acid. Okay, so I already put that on the board. Just the point that I want to make here, again, is that no matter whatever else happens in that solution, this reaction is always going on. It always has to be considered. Okay, so when this reaction happens in pure water, then what's the concentration over here? Right? If this times this equals that, and it comes from this only, then these two concentrations have to be equal. Right? So how could they be equal and give you that value? Well, this one would have to be 10 to the minus 7, and this one would have to be 10 to the minus 7. Molar, of course, molar. So that way, 10 to the minus 7 times 10 to the minus 7 is 10 to the minus 14. In this case, both of these being 10 to the minus 7 molar, that's a neutral solution where these values are equal. Now, under other circumstances, maybe a change in temperature, these concentrations might be different. But if you start with pure water, they will always be equal and the solution will always be neutral. That's the condition. If the hydrogen ion concentration and the hydroxyl ion concentration at equilibrium is the same, is equal, then you have a neutral solution. And the expression there substitutes hydrogen ion here instead of the hydronium for convenience. Now, if you have a situation where the hydrogen ion concentration exceeds the hydroxyl, then you have an acidic solution. And it's going to have all the characteristics of the acids. If you can taste it, right? They don't recommend that, but vinegar is an acid, right? Taste it, it tastes sour. Now, how do you get there? You don't get there from here and here like that. There's no way. But if you add a source of hydrogen ions to solution, then you can unbalance the equilibrium in favor of the hydroniums, of the hydrogen ions. In that case, you have an acidic solution. You can go the other way if you add hydroxyls, and then the hydroxyls will exceed the hydrogen ions, and you have a basic solution. And it has all the characteristics of a basic solution. It tastes bitter, right? If you can taste one, right? Most medicines that you take have are in gel caps, or they're encapsulated. One reason, of course, is to make them pass through your stomach without being destroyed, and then they disintegrate in your intestines where they can be absorbed. But also another reason is you don't want to taste those things, because most medicines that we're given today are basic in nature. They have a basic, they have an excess of hydroxyls that are produced when they go into solution. So they're very bitter. I mean, just let almost any medicine, let it dissolve on your tongue and you'll be sorry you did. It will taste horrible. Okay. So what's the equilibrium constant expression for an acid acting in water? There it is right there, just like I drew on the board. Okay. If the equilibrium lies to the right, the value of K is very large. Right? And if it lies to the left, it's very small. Now, I'm not going to say that the Ka, well, in this case, maybe it is. The Ka would be greater than 1 if it were equilibrium laid to the right, and less than 1 if it lies to the left. Simply because these are 1, 1, 1, and 1, right? You don't have a complication from exponents. Right. We couldn't say that about equilibrium in the previous chapter because we had the influence of those powers of each of the concentrations. But when we're talking about acids and bases, this is a fair statement. If it's greater than 1 or large, then equilibrium lies to the right and vice versa for the left. Okay. So in this case, let's see, let me modify this one. Let's make this HA. and this A minus. There we go. Okay, if water is a better base than this one, which means what? Well, if what it says water is the base. If water is a better base than that, then what's that mean? That means it can accept protons. Right? So like that, oh, excuse me, that's not right. Like that would yield the dihydronium. And this one would yield another acid. So it actually goes back the other direction. All right, so if water can accept a proton more strongly than this one can, then which way is it going to go? If this is a stronger acceptor of a proton than this one is, it should go that way, right? Should go to the right. In favor of products. Does this mean HA is strong or a weak acid? Well, it's probably strong, but it doesn't have to be very strong. It just has to be a stronger acid than water is. Right. And for simplicity's sake, we're just going to say it's a strong acid. So is the value for Ka greater than or less than 1? It should be greater than 1. It's headed that way. Okay. Now let's see if we can make sense of this scenario. So we want to put these in order of strongest to weakest base. So we have to say, okay, if water is a base, right, that means it has to accept a proton from somewhere. So water doesn't really want to accept a proton. It's a very weak base. But this one is even weak. Let's see. A minus from a weak acid, A minus, and the other one we have is this one. Okay, this is the easy one. Cl minus comes from, in our scenario, comes from HCl, strong acid. Right, so if this is from a strong acid, HCl produces that plus this. If this is strong, that's going to be very weak base. It's going to be the weakest base. So chloride is going to be way over here. We just have to decide what goes here. Does A go here or does A go there? Well, if A minus is from a weak acid, that means it's a strong base. So more than likely, it's going to be here and water is going to be in the middle. Yeah, that's what the authors think also. All right. Okay, consider a solution of Na, where A minus is the anion from a weak acid. Okay, in this situation, rather than add the acid as HA, we only want to add the conjugate base. So the conjugate base of HA, remember, is A minus. So if this one is a weak acid, this has to be a strong conjugate base. Okay? So if it's a strong conjugate base, the reaction that's going to occur when you add this one to the solution by way of this, actually, it produces these two ions, and this salt is completely soluble. That means it's not coming back this way. It's going all the way to the right and producing nothing but that. Now this is free to react with water, because that's the only other compound that's there that has a proton in it, and it will dominate in this direction. Okay, so the equilibrium for this one, oh, now we have another equation, right? Because now we have this in solution. It may be derived from this, but it's actually its own reaction. A minus reacts with water and produces HA plus OH. Okay, so when we put this in solution, as we did with sodium A, then we end up with a basic solution. And that means, since this is a very strong base now, because it's the conjugate base of a weak acid, the reaction wants to be far to the right toward the products. No, that's wrong. I inherited these slides from the publisher, and several of them they got wrong. This equilibrium should lie to the right. Okay. So let's consider this same reaction again. How about the value for Kb? Well, if it's going to lie to the right, the Kb has to be large, greater than 1, shouldn't it? Yeah, it should be far to the right. It should be greater than 1. Okay. So here we have the same reaction derived from a weak acid, so we have a strong base. Does this mean A minus is a strong or a weak base? Well, I've been saying it for the past 10, 15 minutes. No, it's a strong base. A minus would be a strong base if it's derived from a weak acid. Okay. Now we got another brain teaser. So if we have acetic acid, HCN, hydrocyanic acid, they're both weak acids. Acetic acid is stronger than HCN. So if acetic acid, C2H3O2, and I'm going to use the abbreviated form here. Just put the proton there and the acetate ion here. Okay, and then HCN would dissociate this way. Okay, now if this is a stronger acid than that one, that's what the premise is. This is a stronger acid than that one. This would be a stronger base than that one. Right? Stronger base. So let's arrange these bases from weakest to strongest. All right. The easiest one to do is chloride. Chloride comes from a very strong acid, so it's the weakest base. So weakest to strongest, we've got chloride first. It's the weakest. I think I need another marker. Okay. How about the strongest base? The strongest base is probably this right here, CN. And then the next one would be acetate. Yeah, acetate ion. And then water. So let me see if they agree with me. Yeah, they agree. But they've also got some other logic involved here. So if you're actually given values for the dissociation constant, the Kw for water is 10 to the minus 14. And the Ka for acetic acid is 10 to the minus 5. the Ka for hydrocyanic acid is 10 to the minus 10. So, if we're treating this as a base, I think, right? Yeah, as a base, then it's not very attractive for protons. That's because its Kw is 10 to the minus 14. Well, the Ka for these is one value, but the Kb for, well, the Ka for the acids here are at a certain level, but the Kb would be much smaller in the other direction, which means that the reaction would be favored for attracting a proton. It's kind of hard. Until we learn how to calculate Kb, it's difficult to explain this. So I think we got, let me check my hard copy here. Yeah, it's coming up right around the corner. How to calculate the Kb. So let's do that. Let's move on, and it should fall into place as we talk and listen. I'll tell you what, I'm going to skip ahead. No, I better not. Let's take these slides in sequence. I think that'll work best. What's the value of K for this reaction? Notice now, instead of having just an acid or just a base reacting, we've got an acid and a base reacting. So for this reaction, we want to find out, we want to estimate, is the K greater than 1, less than 1, or equal to 1? Okay, so notice that this is an acid dissociation from here to here. So the proton is being transferred to this base. Well, if the Ka for this one is 10 to the minus 10, and the Ka for this one is 10 to the minus 4, then this should make a weak base here, and this should make, since this is a stronger acid, this should make a weaker base. This is a weak acid. No, excuse me. This is a weak acid, very strong base. This is a stronger acid. This is a weaker base. So I would expect the reaction to be more toward this side. Oh, okay. I didn't realize I had a slide here that was going to explain this. Okay, so there are your Kas, and there's your reaction. Let's see, this is 6.2 actually, 6.2 times, and this is 7.2. And this is the Ka. This is the Ka. All right. So the Ka for HCN is very small. That means the strong drive is toward here, this side. The Ka for HF is small. The strong drive is to remain for this side. So there's a competition with which side wins, which one wants to stay on its undissociated side. So since the Ka for HCN is much smaller than the HF, then the HCN wins the battle. It wants to stay here more than this one wants to stay there. That's what these comparisons are doing. In fact, It's 6 orders of magnitude weaker than this one is. So it wants to stay over here toward the reactant. So our K should be much less than 1. Okay, that's a semi-quantitative approach. And we haven't done any calculations yet. You can actually calculate what the K for this reaction will be. So I think that's what we've got coming around the corner here. But first, what we want to do is, right, what would be the KB expression for this one? Right, if we know the Ka for that one, the Ka is based upon this, correct? HF yields H plus F minus. That's what this one refers to right here. What would this one be? Well, now we're talking about not, this is the Ka for the dissociation of that one. When we're talking about Kb, we're actually talking about F minus reacting with water, not with HCN. And that would give us our HF again, but now it gives us hydroxyl. So this is the Kb, right? Not this reaction, but this reaction is the Kb. Okay, so now we have to say, all right, we're going to work with generic acid here. HA equals A minus plus H plus. Okay, so there's your expression for the generic acid, the K, the acid dissociation constant for that acid. All right, if we put just the A minus in solution, then it's going to react with water. This is the expression for the reaction for the base. The conjugate base of HA is A minus, put it in water, it reacts that way. What's the expression for that? Well, the base dissociation expression is HA times OH, right? Divided by that. So how are they related? Well, if we add them together, what do we get? Okay, let's do that. Add those two together, just like we were doing Hess's law. Right, HA's cancel, and the A minuses cancel because they're on opposite sides of the arrow. And what do you have left? You have the dissociation of water. H2O yields H plus and OH. Well, when we do this addition, what happens to the equilibrium constants? Well, when we combine equilibrium constants in a Hess's law addition, you multiply them. So Ka times Kb equals the dissociation constant for water, which is Kw. So Ka times Kb equals Kw, and that's also equal to hydrogen ions times hydroxyls. So if we have a Ka value for this acid, we can calculate the Kb value for that conjugate base. Okay, so it would be what? It would be, let's see, Ka would be 7.2 times 10 to the minus 4 times Kb equals 1 times 10 to the minus 14. That's Kw. So all we have to do is say, divide this one by that one, and you get Kb. There you go. Or if you have Kb and you want to find Ka, you just divide Kw by the Kb. All right. I think the slide is going to do that for us, so I'm not going to do the calculation. Let's see. So if we break this equation into two competing reactions, what are the competing reactions? Well, there's dissociation of HCN and dissociation of HF, which has to be inverted, right? If we're going to use Hess's law to add them together, There's the K for hydrocyanic acid. And there's the K for HF. Okay. But we need the inverse of the HF reaction. Now, in this case, we actually do take the inverse of that equation, of that reaction. Oh, okay. Zach's on board now. So rather than calculate the KB, we're actually going to calculate the inverse of K for HF. Because now we're looking at the reaction going in reverse. We're going this way for this part from here, here. Because we got to flip our equation in order for it to add together. Okay, so the K for this flipped reaction is 1.4 times 10 to the third. Now on the next slide, we're going to combine the two reactions. Right? That's what we did here. We put them both together after we flipped the HF and calculated its new equilibrium constant. Then we put them together, and now the hydrogen ions cancel, and we're left with our target equation, just like we were doing Hess's law of any other reaction. And then we multiply those two values together, and we get the K for this reaction, 8.6 times 10 to the minus 7. What does that tell us? That tells us that it does, in fact, lean toward the reactant side. In fact, heavily leans, 10 to the minus 7th. Well, actually, it's closer to 10 to the minus 6 because 8.6 times 10 to the minus 7. So it's 6 orders of magnitude difference, just as we predicted. Okay. Now let's learn a little shorthand. If you haven't already been exposed to pH, this is your opportunity. There was a chemist who was interested in expressing hydrogen ion concentrations in calculations and talking about them, writing about them in the literature, but he really didn't want to use scientific notation for these low values for hydrogen ion concentration. For weak acids, for instance. His name was Sorensen. And he came up with this mathematical transformation, and that's all it is. What he did was, he took a hydrogen ion concentration. He said, okay, I'm just going to take the log of it. Right? For weak acids, this is going to be a value with some negative power up here. I don't know, say minus 7. Well, let's just take it for pure water. How about that? 1 times 10 to the minus 7 molar would be the concentration in pure water. So if you take the log of that, what does that give you? Remember the definition of log. You got a base here. Log, that base is 10. What that means is that whatever value we have over here, 10 to that power equals this. Okay? So 10 to what power equals that if this is it? Well, x now is minus 7. Right? 10 to the minus 7 is x. X is minus 7 because that's the power of 10 that gives you this. Right? Okay. He didn't want to deal with negatives either. So he said, okay, we'll put a negative out here like that. Now this becomes positive. And he called it little p, big H. Don't ask me why. But that is an expression of acidity, and it's purely a mathematical transformation. If we had something like, let's see, 10 to the first power molar, like it was a strong acid, and we take the negative log of that, what would that be? Well, let's see. 10 to what power equals 1? Anything to the 0 power is 1. So the pH of that acid concentration is 0. You can even, if we had 2 or 3 or 4 here, right, this would go negative. The point is, this is a mathematical transformation. There's nothing special about it, except that it makes expressing acidity a little less unwieldy. Because instead of a scientific notation and expressing the hydrogen ion concentration directly in that form, you can convert it to an abbreviated form here. All right. So our previous calculation said 10 to the minus 7th is neutral, right? And the value is 7. So pH 7 is a neutral solution. pH greater than 7, because we introduced that negative number, now pH greater than 7 is basic. So if we put it on a continuum here, this is pH and this is neutral. But if we have a higher, a lower acid concentration, let's go higher. A higher acid concentration would be 10 to the minus 6, wouldn't it? That's bigger than 10 to the minus 7 by a factor of 10. Well, what's the pH of that solution? That's a 6. If we went minus 5, minus 4, 3, 2, 1. This is the acid side. We're increasing concentration of hydrogen ions, but the pH is getting smaller. And we go the other direction. Say if that was 8, so that's smaller, that's less hydrogen ion concentration, which now we're in the basic range. And that's typically our useful range, between 1 and 12, or 12 and a half, sometimes 13. And this is the basic range. Okay? These are just examples of some common solutions. Stomach acid is around 2, unless you eat a big Italian meal with tomato sauce, then it might drop down toward 1. Lemon juice is not even as strong as stomach acid. Vinegar is even weaker. Black coffee, not too bad. Milk, now you're getting close to 7. Pure water is 7. Blood, if you've had anatomy and physiology, or maybe even a biology course, you know that the range of pH for a normal functioning human, not in distress, the pH range would be 7.35 to 7.45. Okay, that's normal blood pH. Now we're going to talk about why that is later in chapter 15, my chapter 15, when we talk about buffers, because the blood is a buffered system. In other words, it stays within that range, that narrow range, most of the time. If you go acid, if you go much less than that, then you're going to be in serious trouble. And some diabetics do. They go way below that. And that's when you rush them to the hospital. Okay, so let's move on. So what's the pH for these solutions? Let me see if this one's working any better. So A, the hydrogen ion concentration here for A is equal to 1.0 times 10 to the minus 4 molar. So we need a negative log of 1 times 10 to the minus 4. All right, so remember your rules. A log of a product like this is the same as the log of this term plus the log of this term. Like that. Okay? What's the log of 1? Well, 10 to what power equals 1? It's 0. Okay? So that term drops out. And we're just left with this one. So 10 to the minus 4th with a base 10. So that means this has to be minus 4 with a minus sign plus 4. So this pH is equal to 4. And by the way, significant figures, when you're going backwards and forwards here, significant figures. The number of decimal places, this should be 4.0. Actually, yeah, that's right. No, there it is. The number of decimal places in your pH is equal to the significant figures in the hydrogen ion concentration. So we have 2 significant figures here. You need 2 decimal places there. Okay, so if you're going back the other way, then you got 2 decimals here. That means you need 2 significant figures here. So that was A, pH 4.00, and B, what's the pH of this solution? 0.040 molar hydroxyl ions. Okay, I'm going to give you the long way around first, and that will make the shortcut all the sweeter. Remember that Kw equals hydrogen ions times hydroxyl ions, which equals 1 times 10 to the minus 14. So if we know that hydroxyl is here, 0.040, then all we have to do is divide this one into that one, and we get that one. Okay? So let's do that. One times 10 to the minus 14 and divide by 0.040. That's 2.5 times 10 to the minus 13 is the hydrogen ion concentration. Okay, so now we can calculate the pH. So the pH is equal to negative log of 2.5 times 10 to the minus 13 molar hydrogen ions. So I've already got it in my calculator, just hit log and then change the sign. So pH is equal to 12.6. Now that's the long way around. There we go, and there we go. I'm not sure about that pH. That's right. Yeah. We've got 2 significant figures here. We need 2 decimal places there. All right. So what's the pH of a solution? If the pH of the solution is 5.85, now what's the hydrogen ion concentration? We're going to go backwards now. It's not as bad as it sounds. This is pure math, just logarithm math. So if we have a pH of 5.85, what does that mean? That's equal to the negative log of hydrogen ion concentration. Okay. So we got to get rid of that negative though. So let's move it over to the other side. All right, so let's get rid of this one and let's put the negative over here. There you go. Okay, now what does that mean? That means 10 to the minus 5.85 power equals the hydrogen ion concentration. That's known as the anti-log, or on your calculator, it will be 10 to the X. At least it is on mine. And if you have a log key, an LOG key, then you hit the shift key and move it up, and there's your 10 to the X. So if we hit 5.85, change the sign, and then hit 10 to the X, I get 1.4, let's see, 1.4, right? Two significant figures, two decimal places. So that's equal to 1.4 times 10 to the minus 6 molar. All right. That's how it's done. Okay. Now, like I've been saying all along, this negative log transformation to make pH is just math. So we could invent another transformation if we know the hydrogen ion, the hydroxyl ion concentration in molarity. Then what if we say negative log of that? That's equal to the POH. Correct? Works for me. Okay. Now, suppose we have this expression. KW KW equals hydrogen ion concentration times OH concentration. And that's equal to 1 times 10 to the minus 14 molar. No, that's not right. That's the equilibrium, so we don't put units there. Okay. What if I'm just kind of spitballing one day and I say, what if I take the negative log of that whole equation? Right? So I say negative log of KW equals the negative log of hydrogen ion concentrations. Right? If we're going to take the log of a product, what does that mean? Well, it's the log of this one plus the log of that one. So plus the negative log of hydroxyls equals what? The negative log of that is 14, isn't it? Negative log of 10 to the minus 14 is 14. So this would be PKW. This would be pH. This would be POH. And this would be 14. So PKW equals 14. pH plus POH equals 14. So if you calculate the POH and subtract it from 14, you'll get pH. This is the shortcut I was talking about before. There it is in animation. All right. So in a neutral solution, 7 plus 7 equals 14, right? pH of 10 to the minus 7, POH of 10 to the minus 7 equals 14. Okay. Now, we want to calculate the POH for these two solutions. We did these earlier. Not exactly like this, though. If A equals 1 times 10 to the minus 4 molar hydrogen ion concentration, then the pH equals 4, and the POH equals 14 minus 4 equals 10. Right? Well, let me see. It needs 2 decimal points, doesn't it? Right, because we have 2 significant figures here. Okay, how about this one? If 0.040 molar equals hydroxyl ion concentration, then what's the POH? Well, the POH equals negative log of 0.040. All right, so let's do that one. 0.040, take the log and then change the sign. Let's see, we got two significant figures. We need two decimal places. 1.40. That's the POH. So now the pH, did it ask for that? I just said POH. Okay. So there's the POH for this one. There's the POH for this one, 1.4. But if we wanted to know the pH, we just say 14 minus 1.40. And that would be 12.6. Okay. pH of a solution is 5.85. What's the OH for this solution? We calculated the pH before, didn't we? But I can't remember what it is. So we'll have to do it again. So if we say what we want is the anti-log of negative 5.85, which is 10 to that power. $1.4. Oh no, I'm sorry. What am I doing? I don't need to know the hydrogen ion concentration. I want to know the POH. Or what's the hydroxyl ion concentration? So we need to do this first. 14 minus 5.85. Right. And this is a, my mind's gone blank. This is the limiting factor on the number of decimals. So we have 5, 1, and 5 from 13 is 8. 8.15 is POH. And then we take 10 to the minus 8.15, which is the antilog of the negative, and that should be 7.1 times 10 to the minus 9. Molar hydroxyl ion concentration. All right. Okay. We're going to start moving into equilibrium calculations. I'm talking about ice tables in large part. Trying to determine the pH of a solution of a given mixture of acids and bases, or conjugate acids and bases of any kind. So what we want to do first is decide what are the major species. Remember, this water reaction, water plus water equals hydronium plus hydroxyls, it's always there. So we have to consider that in our calculations when we're setting up the problem anyway. But that's not the only thing we consider. We're looking for major species. What are the big actors? What's going to dominate? And then we look at the reactions that they might occur in the solution, and then compare those reactions and see which ones make sense, and then which one dominates before we can even solve for the pH of the solution. Now for this one, 2.0 times 10 to the minus third molar hydrochloric acid. What are the major species? Right? There's no HCl in there, right? This is a strong acid. It completely dissociates into hydrogen ions or hydroniums, chloride ions, and there's always water there. Those are the major species. So the pH is based upon hydrogen ions only. There it is, 2.7. That's the nice thing about strong acids. When you put a strong acid in solution, that's an immediate concentration calculation and conversion to pH. How about this one? What's the pH of 1.5 times 10 minus 11 molar? Well, let's see. Major species again. HCl doesn't exist anymore. So we take 1.5 times 10 minus 11, take the negative log of it, and you get 10.8. Now, what does that say about the solution? That says that it's basic, right? The concentration of hydrogen chloride or hydrogen ions in that solution is less than neutral. Neutral will be 10 to the minus 7. 10 to the minus 11 is 4 orders of magnitude less. So yeah, it's a basic solution. Okay, what if we add HNO3 to water? Well, the first thing that happens is proton is transferred from that strong acid to water. So we're essentially all the way to the right. That's not likely. Why? Because NO3 minus is an extremely weak base. It does not accept protons. So that reaction is not even considered. This reaction is always going to occur, right? The self-ionization and the acid-base reaction of water with itself. But is it a major contributor of hydrogen ions? Well, in this case, no, it's not. So if we do have a solution that's this concentration, all we really need to do is take that concentration of nitric acid and calculate the pH, negative log of 1.5 times 10 to the minus 2. So these examples we've been dealing with for the past couple of slides are all strong acids, right? And that's telling us that they are the major players. The strong acid dictates what the pH will be. So here's a series of steps that you would go through to solve an equilibrium problem with a weak acid. So again, you're going to find the major species that are involved, choose those that can produce hydrogen ions, and write the balanced equations. Then if you have them available, well, you should have, the equilibrium constants for those reactions and decide which equilibrium will dominate in producing hydrogen ions. And then write the equilibrium expression for that particular reaction, and that's the one that you'll use to determine the outcome of the reaction with your ICE table. Then once you write that reaction out, like I like to do, and then put the ICE table here and initial concentrations, and then work your way down to equilibrium so that you can concentrate, so you can calculate the hydrogen ion concentrations. Now, one thing you do want to do is, if at all possible, just like the other equilibriums that we've dealt with, is choose your unknown, the X value, so that when you solve for X, that gives you the hydrogen ion concentration. If at all possible. You may not be able to do it, but if possible, do it, then that saves you a step. And then we introduce this 5% rule here, just like it was in previous equilibrium expressions, right? If we have to make an estimate, if we have to say, okay, in this case, we're saying the concentration of X is so much less than the concentration of HA in an expression, then we can drop the X and say it's essentially equal to HA. But if we're being strict with ourselves, then we'll need to recalculate the dissociation constant, the K for that reaction, with our new values and see if it's close to the accepted value. If it's within 5%, then our answer is good, and we can calculate the pH from our hydrogen ion concentration. Okay, how about this one? 0.8 molar weak acid, HCN, hydrocyanic acid, and there's the Ka again. What are the major species? Right? We're not going to take this one all the way through. We're just doing the preliminary steps. What are the major species? Well, HCN does not dissociate very much, so it's HCN as a major species. And of course, water. And that's all we have. Right? Those are not major species, H plus and CN minus. HCN reacting with water, based upon this value, the Ka for the HCN versus the Kw for water, says that this is the dominant reaction. 10 to the minus 10 is 4 orders of magnitude greater than 10 to the minus 14. So this is the dominant reaction up here. That's the one that controls the pH. Okay, so that's as far as we're going to go with that one. Now we're going to switch gears. We're going to pick a different acid, HF, hydrofluoric acid. This is a stronger acid than hydrocyanic acid, but it's still a weak acid because its equilibrium constant is 10 to the minus 4. That also, I want to make a point here. HF, in chemical terms, is a weak acid, right? But if it's very concentrated, and I've used concentrated hydrofluoric acid before, if it's very concentrated, then this stuff is nasty. It is very dangerous. Even though it's a weak acid, when you get that much of this stuff all in one place, it has a tendency to eat its way through anything biological, right? If you take concentrated HF and just put a few drops on your hand, it won't stop eating until it comes out the other side. And that's partly because of its acidity. Being a weak acid, only very concentrated, it produces lots of hydrogen ions. It also produces lots of fluoride ions too. And the fluoride ions react with your skin and your bones, and it will go straight on through. Okay, back to the topic here. So if we have a solution that's 0.5 molar in HF with that Ka value, then what are the major species? Well, HF is, and H2O, just like similar to the last one. So we compare the reaction Kas, and we find that the controlling one is the HF. Okay, so we set up our ice table, right? We know that we start off with 0.5 molar, and there's essentially no hydroniums and no fluorides. There might be a few floating around, but they're not controlling the pH. So we're going to lose some HF, and it's going to show up over here, like it's 1 to 1 to 1 to 1. So if we lose some over here, we gain exactly the same amount on the other side. So at equilibrium, we have 0.5 minus X, and then we have X hydroniums and X fluorides. Okay, now we set up our equilibrium expression. There it is. There's the hydrogen ions, there's the fluorides, and there's the HF, and that's all equal to 7.2 times 10 to the minus 4. Then we fill in our unknowns, right? There's X here, and 0.5 minus X. Here's where we make our estimate. Since the K value is so small, 10 to the minus fourth, then X is going to be insignificant. That's our assumption. So we assume that 0.5 minus X is essentially the same as 0.5. So we set it up that way. And what that does for us is it allows us to do the calculation without having to deal with quadratic solutions. So we calculate X to be this value and the pH to be 1.72. Now, 1 second. Yes, I'm just checking. My next slide is going to do the 5% comparison to see if this assumption that we made is valid. Okay, so on the next slide, we find that, okay, this is our expression. So what if we take the X value that we determined and plug it in to the unaltered version, 0.5 minus X. So we're going to put in the X value here, here, and here, and do the calculation, and that is the calculated value for Ka is 7.481 times 10 to the minus 4. So then we compare this one, compare this one to the accepted value and say, all right, is that less than 5%? So we say this one minus the accepted divided by the accepted times 100 is 3.9%. We're good. Our assumption was essentially correct. Now, you can also use a method. We could start from this point. And we could take that value, 1.897 times 10 to the minus 2, 1.897 times 10 to the minus 2 for our X. And when we do the ice equilibrium calculation, instead of leaving that X in this expression, X times X over 0.5 minus X, instead of dropping that X, now let's put this value into it. 1.897 times 10 to the minus 2, here we go, is equal to 7.2 times 10 to the minus 4, and now solve for X. This is a procedure, a method called successive approximations. So let's just calculate that X out. Okay, let's take this one. There we go. 0.5 and subtract this one from it. 1.897 exponent minus 2. Okay, that gives me 0.481. And then times this one. Take this one times that one. Okay, I need more decimal places. Hold on a second here. Display. Scientific. 6. There we go. So now, when I multiply this one times this one, that gave me 3.463 times 10 to the minus 4, and that's X squared, X times X. So I just need to take the square root of both sides. So now X, by this calculation, is 1.861 times 10 to the minus 2. Okay? Now we can do this same calculation again and say, all right, we're going to say that now we're going to say X is this value, not that value. And if we say 1.861 times 10 to the minus 2 times itself, which would be squared, over 0.5, yes, minus 1.86 times 10 to the 1.861 times 10 to the minus 2. And what's that equal to? Well, let's see. I've already got this one in the calculator. I'm just going to square it. And then I'm going to subtract this one from that one. There we go. Nice. And divide it into this one. And that gives me 7.19 times 10 to the minus 4. Okay. So I don't even think we need to do the calculation. What's the accepted value? 7.2. If we rounded this one off to 2 places, it would be 7.2. So this successive approximation took our first estimate and then reused it to do the calculation again, and it got us even closer. So this is a better approximation for X, or the hydrogen ion concentration, than this one. Okay, successive approximation. There are some times when that's the only way to solve a problem. And if you have your computer program set up right, it's not that much trouble. Okay, so did it ask us what the pH was? No, it didn't. What would be the pH for this one? If we take this value, 1.861 exponent 2, and then take the log of it and change the sign, that's 1.73. Now let's go back. I think 1.72. Okay, so we were off by 1/100th with that first approximation. So it's really not that big a deal. If you're under 5%, then you got a good number. Okay. Now here's another concept. It's called percent dissociation or percent ionization. All that means is when you have this acid and it's dissociating into its hydronium ions and conjugate base, you want to know how much of this did you lose. Okay, if you have a concentration here of, I don't know, 1 molar, and you end up over here with 0.1 molar after the reaction, then that means you lost 0.1 molar, and this is actually 0.9. So the dissociation is you actually dissociated 0.1 molar, 0.1 molar out of 1 molar. So that's 10%, right, times 100. That's the dissociation that we're talking about here. How much did we lose in the dissociation, percentage-wise? Okay. Now, here's the part that gives students a problem. For weak acids, this is just for weak acids. As you decrease the concentration of the weak acid, you find that the percent dissociation goes up. Now, that doesn't mean that you got more hydrogen ions in solution. It just means that a larger percentage of the acid dissociates. We're going to go through a couple of slides here that hopefully will make sense of that. Okay. So this is what would happen with formic acid, HCHO2. Formic acid. If you've ever had a close encounter with a fire ant, you know what formic acid is. Formic acid is one of the chemicals in that cocktail that they inject into the wound that makes it sting so bad. In fact, the name formic acid comes from the Latin for ant. The part of it, form, F-O-R-M, is derived from the Latin for ant. Anyway, let's say we have a solution of 8 molar formic acid, and we're given that it, in water, it ionizes by 0.47%. So that's the percent dissociation is 0.47%. So what does that mean in terms of fractional multipliers? Well, a percent is parts per 100, right? So how much would it be parts per 1? And if it's 0.47 parts per 100, then it would be 0.0047 parts per 1. So this is your decimal multiplier. That's why that value there in the change row is 0.0047. Right? So whatever disappears from the CH2 and becomes hydrogen ions and formate ions is that multiplier, gives you what's lost from one side and what's gained on the other side. Okay, so up to this point, we've done the calculation. So we have an equilibrium calculation here, and we're going to calculate what is the Ka for formic acid based on those figures. Okay, there it is. So we calculate our Ka here to be 1.78 times 10 to the minus 4. So it is a weak acid. But now we're going to use that K that we just calculated to go a step further. So what's the pH of an 8 molar solution of formic acid? Well, we calculated the concentration of hydrogen ions here, right here, 3.76 times 10 to the minus 2. So the pH is just the negative log of that value at 1.42. All right. Now, the value of Ka for a 4 molar formic acid solution should be what? Should be less than, greater than, or the same as the Ka for an 8 molar solution. That's kind of a trick question. K is a constant. If you don't change the temperature, the K is constant no matter what the concentration is, just like equilibrium in the past chapter. Right? So it's going to be the same as. However, the percent ionization of 4 molar solution, we've decreased the concentration, so the percent ionization will go up. So it'd be higher than the percent ionization for 8 molar, right? It was 0.47%, wasn't it, for 8 molar? 8 molar formic acid, excuse me, let's see, C2 I lost it. There, I think that's it. I have to draw the structure to know if I'm right. Formic acid is like this. It's 2 hydrogens, 2 oxygens, 1 carbon. Okay, I'm good. All right. So, oh, they're going to use a generic acid. Well, that's all right. What if we have a weak acid, HA, with an initial concentration of HA sub 0, right? That's what that little 0 means. That's the initial concentration, and they're at equilibrium. Okay, this is the equilibrium expression for that acid dissociation, and there's the Ka in the generic form. So let me move this a little so I can see what's going on. There we go. So HA is approximately equal to HA minus X, or HA is equal to, HA0 is equal to HA. That's because the dissociation is so small. We're saying that they're essentially the same. So the concentration of hydrogen ions and the concentration of conjugate base are equal, and they're equal to X. And that's based upon that previous ICE table. It works the same way for every acid dissociation. So there's our expression for the initial conditions of the Ka dissociation. So what would happen if you added enough water to reduce the concentration of HA by 1/10? What would that do to the expression? Okay, let's see. Right, here's the new concentration of the conjugate base and the hydrogen ions. It's X over 10 now, right? We've decreased by 1/10. And we've also decreased the new HA by 1/10. Okay, so now we've stressed the system. Remember, Le Chatelier's principle, we have stressed the system by changing concentrations, by adding this water, and reduce the concentration of the products. Which way will the reaction proceed? We've diluted the products so that they're going to try to make more product. And here's what the expression would look like. Right? If we calculate Q for this reaction, even before the equilibrium is established, right, we have new values of X, the A minus and the H plus here, and then the HA here. Right? So then we can factor out 1/10 from this reaction. So what we find is that the new K, well, not the new K, the Q would be 1/10 of the Ka. So if the Q is smaller than K, which way is the reaction going to go? That means you don't have enough product. So if the Q is smaller than K, that means you don't have enough product. It's going to shift to the right. So when it shifts to the right, the percent dissociation increases because you have to dissociate more of the acid in order to get that movement to the product side. So that's the explanation for increasing the percent dissociation with a decreasing concentration. So the pH should be higher. Even though you are dissociating more of the acid, you've also diluted it by a factor of 10. So your hydrogen ion concentration actually goes down, which means you have an increased pH. All right. So if we calculate the percent dissociation based upon 4 molar, right, so X now is equal to 2.66 times 10 to the minus 2. Come on, there we go. And calculate the percent dissociation using that value, then, yeah, it's 0.67%. So for 4 molar, this was 0.47% dissociation. And for 4 molar, we had 0.67% dissociation. So that's a quantitative, not explanation, it's a quantitative evidence for our previous assumptions. So what would be the pH of a 4 molar solution? Well, we calculated the hydrogen ion concentration. So all we have to do is take the negative log of it. And it's 1.57 versus, what was it, 1.4 something? 1.42 pH versus 1.57. So the pH actually did increase. Not by much, but 0.15 pH units. Now remember, pH is a logarithmic scale. So if the hydrogen ion concentration goes from 10 to the minus 7 to 10 to the minus 8, that's a pH of 7 to 8. But the hydrogen ion concentration has gone down by a factor of 10. Okay? So every 1 pH unit, you have a factor of 10 change, either up or down, depending on which direction you're going. So this little difference here, it looks like a little difference, but it's a significant amount of hydrogen ions that have changed concentration. All right. We talk about bases a little bit. Okay. Arrhenius bases, just to review, Arrhenius base requires that the molecule contain an OH polyatomic ion in its makeup that can be dissociated. Whereas Bronsted and Lowry says, all we want is something that will accept protons. Well, an Arrhenius base will fit that definition too, because hydroxyl ions will readily accept a proton, right? When you consider water as a very, very weak acid, that means hydroxyl is a very strong base. Okay, so what are some strong bases? Well, by the same definition as strong acids, these bases completely dissociate in water. Lithium hydroxide, sodium, potassium, calcium, those are alkali metals and alkali earths hydroxides. Okay, what's the pH of a solution that's 10 to the minus third in sodium hydroxide? Well, calculate the pOH first and then subtract it from 14, right? So there's your 3, subtract from 14, and you get pH of 11. That pH is greater than 7, which means it is basic. How about calcium hydroxide? That's a little bit different. If you have a 10 to the minus third molar solution of calcium hydroxide, what does it dissociate into? Well, it's got calcium 2+, but it's also got 2 hydroxyls. Right? So that means that the concentration of hydroxyl is actually 2 times 10 to the minus third. The pOH then would be 2.70 and the pH would be 11.3. So it's a little bit higher pH, right? It was 11 for the previous one, which was lithium. Sodium hydroxide. But calcium hydroxide bumps the pH up a little bit more because it has 2 hydroxyls for every molecule. Okay. So now we're going to go back to pick up with the expression Kb. So whenever you see the expression Kb, you know that there's a base reaction going on. So the Kb says that the species that you're starting with reacts with water. And when it reacts with water, it accepts a proton and becomes the conjugate acid of the base and leaves behind usually a hydroxyl. And the expression then looks something like this, at least for the hydrocyanic acid. Right? So the products over the reactants. And there's your Kb. And we know how to calculate Kb now. we just say Kw divided by the Ka for the acid will give you the Kb for the conjugate base. Here's an example. Calculate the pH of 2 molar solution of ammonia. Right, so the Kb for ammonia, notice that this is a Kb expression because ammonia is accepting a proton from water and making ammonium ion the conjugate acid and hydroxyl the conjugate base of water. Okay, so they skipped the ice table, but it's built the same way as the acid table, the acid ice table, and we find that this is X, and this is 2 minus X. Right. Do I need to put that on the board? Maybe I should. So here's your reaction. Hydroxyl, there we go. So now our ice table looks like this. Don't need one for water. And we're starting off with 2 molar right here and nothing here. So what do we get? Well, we're going to get an X over here and an X here, right? 1 to 1 to 1. And this is going to be 2 minus X. Excuse me. This is going to be minus X, and the equilibrium will be 2 minus X, and this will be X, and this will be X. So that's where they get the expression. Now we put X times X over 2 minus X. And since the Kb is so small, we're going to say that X is very small. So we're going to eliminate the X and do the calculation and find out what the concentration of hydroxyl should be 6 times 10 to the minus 3. And the POH would be 2.22. Excuse me, POH would be 22. pH would be 11.78. Okay. Notice we did not do the 5% calculation. It's usually pretty safe if your equilibrium constant is 10 to the minus 4, 10 to the minus 5, or smaller, then you're usually pretty safe in making this calculation and not have to go through the 5% calculation. Okay, polyprotic acids. Now we're going to go bases. We're going to go back to acids. What's a polyprotic acid? Well, it's one that has 2 or more protons available to dissociate. For instance, let's see. Well, monoprotic acid would be like that, or like this, right? It's only got 1 proton. Polyprotic would be something like this, H2SO4, or maybe H3PO4. Those are 2 good ones. Let's use this one right here. Okay, H3PO4. We're going to use the simplified version. Rather than transferring a proton to water, we're just going to say the equilibrium setup would be like this. And what's left over? H2PO4 minus. Notice that when we write these reactions, dissociations always occur 1 proton at a time. So we lose 1 proton here, that's an equilibrium. And we're going to say it has a Ka of 1. That's the first one. The second one would be this one, H2PO4 minus. Now dissociates another proton. And what's left? PO4 2 minus. And that also has a K, a different K. And then we'll take one last time, this HPO4 2 minus, and it's in equilibrium with these species, PO4 3 minus. And it has an equilibrium constant. Okay? So that's characteristic of polyprotic acids. They dissociate 1 proton at a time, and each dissociation has its individual dissociation constant. What we also notice is that the values of these Ks, is this thing It's like, hold on a second. I don't know if it's recording the whole board. Should be. Oh, my mistake. Yeah, we're good. So what we notice is that this one is the largest one of the three. It will be bigger than this one. And that one will be bigger than the next one. Okay, so that means that this equilibrium produces some of these, but the next equilibrium produces even less of products, and this one produces even less. So for most polyprotic acids, the dominant dissociation is this one. That controls the pH. And the reason is really simple. You're trying to remove a positive ion from a neutral. Okay, there's some attraction there that holds it, but some can come off. Once you've established this negative ion, and these are polyatomic ions, once you've established this ion, it's more difficult to remove a positive charge from a negative. There's an attraction there. Right? And then with an even larger charge, it's even harder to get the last one off. So that's why the sequence is largest, next, next. And there are the real numbers for phosphoric acid, right? There's a 5 orders of magnitude difference between each one. 10 to the minus 3 to 10 to the minus 8 is 5 orders. 10 to the minus 8, 10 to the minus 13 is another 5 orders. So there's a huge difference between them for this acid. Now, if we could find an acid that had Ks that were very close to each other, like if this were 10 to the minus 3, and this were 10 to the minus 4, and this were 10 to the minus 5, then these two would be significant contributors to the pH overall. I don't think of any examples, but if we could find one with those values close together, not such a wide spread, then the subsequent dissociations would have an impact on the overall and the pH. Okay, so if we have a 1 molar solution, then that would be our expression. And we would discover that the hydrogen ion concentration was this, and the pH was, we're going to do the 5% calculation. Okay, let's do that. 5% calculation. So this is our calculated value for the K, and we compare that to the accepted value for the K. And as it turns out, we're a little high. Yeah. What was the value for Ka sub 1? It was 10 to the minus 3, right? It's not 10 to the minus 4 or 10 to the minus 5. It's 10 to the minus 3. So when they 10 to the minus 3 seems to be the breaking line. If it's 10 to the minus 3, then you're going to be greater than 5%. So what do? Well, you either solve it quadratically or you do a successive approximation. And I think that's what we're going to do next. Yeah. So if we plug X into this expression on the previous page, right down here, plug it in there, instead of eliminating it, put that value in X and then recalculate the X. And if we do that, there's our X value. And then we do our 5% rule again, and we find that it's way below 1%. So we're good. So rather than having to go back and do the quadratic calculation from the beginning, we just use a successive approximation, and that gets us really close. Okay, so what would be the pH? If in fact the first dissociation is the pH controlling reaction, then we can do a calculation of our pH from that latest value that we determined for hydrogen ion concentration. and that's 1.08. Now, what if we were going to try to calculate PO4 3 minus? This one, the concentration of this left over after 1 molar dissociates. All right. So our first step would be to calculate how much of the HPO4 is available for the next step. And that's what we're doing here. So X would give us here. There we go. So there's our, oh, what is that telling us? Oh, that's telling us that our initial concentration, 8.2 times 10 to the minus 2, cancels out, and X is going to be the same for all the reactions, every step. So here we go. There's the hydrogen ion concentration. So hydrogen ion concentration, if we now go to the final equation here, we're saying that the hydrogen ion concentration is this one, which is essentially the original, right? And then we put that one in, and we know what H2PO4 2 minus is, 6.2. We got that one from, where is it? Oh, hold on a second. Okay, there it is. So where did that, oh, duh. That number came from here, right here. So now that we know that this value is 6.2 times 10 to the minus 8, and this one is essentially the same as the original, then we can calculate the PO4 3 minus. And it's very, very small, as we would expect, right? Because if this is a very small value, that's a very small value, and this one, but this is smaller than this one, and this one's smaller than that one, the reaction is predominantly going to be here. We're going to have very little down here. So 10 to the minus 19th molar is not surprising. Okay. So what do we get with an acid-base reaction? We've been talking about acids separate, bases separate, and what they do. Now what if we do a titration, right? We'd add an acid to a base. All right. So if we add an acid to a base, this is definitional. If we had an acid to a base, and we're going to use the Arrhenius definition for simplicity, it still works for Bronsted-Lowry also. What you get is a combination of this cation and that anion right there. Okay. And water, because you get this hydrogen combined with that hydroxyl, H2O. You get water. Okay, so for every acid-base reaction, this is the definition of a salt. In chemistry, a salt is one of the products of an acid-base reaction. It's the combination of the cation with the anion. That's a salt. And water. So those are the outcomes of every acid-base reaction. Acid plus base yields salt plus water. Now, the question is, when we add this acid to this base, what kind of pH can we expect? Well, I'm going to give you the rules of thumb first. The rules of thumb are that if you add a strong acid to a strong base, you get a neutral solution. right? Because this completely dissociates, that completely dissociates, produces nothing but water and salt. No extra hydrogen ions, no extra hydroxyls. All right, that's the easy one. Strong acid, strong base makes a neutral solution. What if your let's see, a basic solution is formed. Oh, if you have a conjugate base of a weak acid. So if this is weak and this is strong, right? And their examples there are, let's see, sodium fluoride. If you add these, put these salts in solution, is what they're saying. So if this salt is the result of a weak acid and a strong base, you get a basic solution. That's the rule of thumb. I'll explain the chemistry behind it in just a minute. On the other hand, if you combine a strong acid, if the salt is the result of a strong acid and a weak base, then your solution will be acidic. Okay? Now, the one that's a little more difficult to deal with is, what if you have a weak acid and a weak base? Well, the only one I can be absolutely certain of is if the Ka for the acid and the Kb for the base, let's see. Yeah, if the Ka for this one and the Kb for that one are equal, then you'll have a neutral solution. But if they're different, then you have to do some mental gyrations. So let me explain why. Let's see. If you have a weak acid and a strong base, resulting from that salt, put this salt in solution as is, what will be the pH of the solution? Okay. So if you have a strong base and a weak acid, then the conjugate base of the weak acid is very strong. Okay? And what then will happen is when you put these in solution, what you will get is an interaction with water that produces HA plus hydroxyl. And that's why it's basic. Not because this was the strong base originator, but because this is the weak acid producing a strong conjugate base. All right. Similarly, what was the example? Strong acid, weak base, right? So HCl would be the source of this one, and ammonia would be the source of this one, right? So strong acid, weak base. All right, so what would this do in solution? This will go into solution. This chloride would have absolutely nothing to do with water. But this ammonia prefers as a, it comes from a weak base, ammonia, so this is a strong acid by comparison. What it would do is interact with water and transfer that proton to water and prefer to be over here. So that's where the acid character comes from, a salt that's derived from a weak base and a strong acid. That's the chemical definition, the explanation for the rules of thumb that I gave you earlier. Okay, this chart summarizes and gives examples for if you have sodium chloride would be derived from sodium hydroxide and hydrochloric acid, which are both strong. So you expect a neutral solution there. Sodium fluoride, sodium hydroxide would be the origin of the sodium, and hydrofluoric acid would be the origin of the fluoride ion. So the fluoride ion is going to be a strong conjugate base, which means it will produce a basic solution when it reacts with water. And I just showed you this one. That gives you an acid solution. This one is an example of a situation where you have okay, this takes some explanation here. Aluminum sulfate. Okay. We would be tempted to say this is derived from sulfuric acid. But when this goes into solution, SO4 2-, that is the conjugate base of a weak acid. This is a strong acid only for the first proton. Right? So this would be associated with that one in terms of HSO4-, and it yields that plus hydrogen. This is a weak acid, so this is a strong base, right? That's a strong base, and what it does when it goes into solution, this SO4 2- reacts with water, and it only goes to HSO4- plus hydroxyl. Right? It won't go back to H2SO4 because H2SO4 is a strong acid. That makes this a weak base. Okay. So that being said, what we need to know in order to decide which one of these is dominant is to look at this reaction and what value would we need for that one. The expression here would be a Kb. The expression for this one, when this one goes into solution, let's see. It could react with water, and that would mean AlOH 2- plus H plus H. Okay. So this value would be the Ka. And we compare those two values. And see which one is larger. The larger one will determine which one of these, whether the basic or the acid reaction is dominant. I don't know if we got examples here. This is just a general rule. If the Ka here, if the Ka for this part of the molecule is larger than the Kb for this part of the molecule, then the pH will be less than 7. It'll be acidic. If they're equal, of course, it's going to be neutral. But if this Kb is larger than the Ka for this one, then the solution will be basic. So it's a competition between the two. All right. So let's see, calculate the Kb values for acetate ion and cyanide ion. Okay, we know how to do that. So there they come. There's the one for the acetate ion, that's Kb. So if you put acetate ion in solution with some countercation like sodium or potassium that will not react with water, then you're going to get the Kb reaction for the acetate ion, and its value will be this one. And for cyanide, similarly, it's going to be that one. Okay. So you'll also see that the Kb for this cyanide ion is much larger than the Kb for that acetate ion. All right. Now what we want to do is, with 1 molar solutions of each one of these acids, bases, or whatever the salts, we want to say order them in terms of lowest to highest pH. So which one would be more acid first, and then gradually work our way up to the most basic. So when I do these, I like to bracket them in. Which would be the strongest acid, which would one be the strongest base, and that sets the outer limits. So are there any compounds composed of ions from strong acids and strong bases? Well, in this case, we're going to set the centered line first. Sodium chloride would be neutral. It would be right in the middle. So we would put it, let me make some room here. So sodium chloride would be right in the middle. And we're going from lowest to highest pH. So this would be a lower pH. This would be the higher end pH. This would be the lower end pH, which would be the acid end. This would be the acid end. This would be the base end. Okay. Okay, so we got that neutral. Now we need to go for, are there any strong or moderately strong bases? Well, I see sodium hydroxide. That looks like to be the strongest base of the bunch. So sodium hydroxide would be out here. It would have the highest pH. And ammonia will probably have the next, because it's not a salt, right? It is a base. So it would probably be next. The next highest pH would be ammonia. All right. Now, are there any compounds composed of ions of weak acid and strong base interactions? Weak acid, strong base. Okay. Weak acid, strong base. Here we go. Sodium cyanide. Cyanic acid, hydrocyanic acid is a weak acid. Sodium hydroxide is a strong base. So that fits right there. So sodium cyanide would produce an alkaline solution with pH lower than this one. All right. There we go. Are there any acids derived from halogens? If the acid is derived from a halogen, it's more than likely strong, with one exception. We've got, let's see, HBr. This would be the strongest acid of the bunch. And then the next one would be HF. Remember, HF is a weak acid by comparison. Now we have to decide the relative position of the two that are left. Ammonium chloride and hydrocyanic acid. All right. Hydrocyanic acid is a weak acid, and it should have a higher pH than HF. While ammonium chloride is a salt of a weak base and a strong acid. So it's going to be slightly acid too. More than likely, it'll be more basic than hydrocyanic acid because it's got a competition between the two cation anions and their acid-base natures. So we're going to put HCN here, and then that would make ammonium chloride. Is that the one we're looking for? Yeah, ammonium chloride should be there. All right, let's see. Here we go. So HBr, HF, HCN, ammonium chloride, sodium cyanide, ammonia, and sodium hydroxide. That's how we would use our rules of thumb to order these. The next possibility is to use the actual equilibrium constants and put them in the correct order. Now we're comparing the Kas and the Kb values. So here are the acids, right here, 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 and here. HBr is a strong acid. It's going to be the farthest to the left. Then the next one is HF at 10 to the minus 4 and HCN at 10 to the minus 10. That's good. Then I'm not sure Ka is the right letter to use for a salt, but it's more likely a K value, which is just slightly smaller than HCN. So that means it's more basic. Then we got the neutral, and now the Kb's come along. Sodium cyanide is a smaller Kb than ammonia, which means this ammonia is more basic. And then, of course, the strong base is the last one. So if we use the Ka, Kb, and equilibrium constants, then we can order them. The same way as before. Okay, let's see. Suppose we put this salt, sodium fluoride, in solution at 0.3 molar concentration. The Ka for HF is this value, 7.2 times 10 to the minus 4. What are the major species first? Well, we're going to have sodium, fluoride, and water, because sodium and fluorine completely dissociate. That's where we start. Those are the major species at the beginning. Okay, these are the possible reactions that could occur. Right? We can react fluoride with water, we could react water with water, sodium with water, sodium with fluorine, and these last two are inconsequential because, well, this one, obviously the bottom one, these go into solution 100%. So it's not going to go back the other direction. And then sodium doesn't react with water. So it's a competition between these first two. So we got to decide which one controls the pH. Well, we need, this one is a Kb. So we need the Kb value because it will tell us, based upon this expression, the products divided by the reactants will tell us if it's a very large number. If it's a larger number than the Ka for this one, then the reaction would be further to the right than this one would be. And that would control the pH. So let's see what we got. That's Kb is 10 to the minus 11th, and the Kw for this one is 10 to the minus 14th. So it's 1,000 times greater. This is the controlling reaction right here. Oh, is that as far as we're going? Okay, they're not going to let us calculate it. We're going to shift gears and go to sodium cyanide this time. see if we've learned anything from the last one. 0.75 molar sodium cyanide with a Ka for HCN of this value. Major species, right, there we go. And we eliminate these last two. So it's a toss-up between the first two, cyanide or water. So the Kb for this cyanide reaction, and notice we have to do the Kb because this cyanide conjugate base is going to react with water. It's got no other choice. So we need the Kb here, not the Ka for HCN. Okay, so we compare 10 to the minus 5, 10 to the minus 14th. We know which one is dominant. It's this cyanide reacting with water. So we set up our ice table, right? Same as always. We plug in our values and say, okay, X is going to be small enough. And this value, 10 to the minus 5, we're probably safe. And calculate that X is 3.46 times 10 to the minus 3. So, and X is what? X is hydroxide ion concentration. So that's the pOH. And we can calculate the pH by subtracting it from 14. There it is. 11.54 pH would be the value for dissolving sodium cyanide in water. Okay. So let's talk about sort of theoretical. What is it that determines the strength of an acid or a base? Two factors contribute to, let's focus on acidity first. Two factors control acidity in a binary compound. One is bond polarity. So for example, if we have this one right there, hydrochloric acid, this bond is extremely polar. Chlorine is more electronegative than hydrogen by quite a bit. Right? So we have a bond that's polar this direction. What does that do for the strength of the bond? It pulls electron density away from the hydrogen, which gives it a slightly positive charge and a negative charge. Well, the stronger this pull, the weaker the bond. So the bond polarity will weaken a bond to make more acidic solutions. So if you want a stronger acid, you want a very polar bond. The other consideration is bond strength. Now, relative to the nonpolar bond, this fact will cause a stronger acid. But the strength of the bond might be very, very large to begin with. For example, HF. The bond strength in HF is very high. Let's see if we've got, we've got a discussion here. The bond strength. So what we find is bond strength alone is the highest for HF. Now that's due primarily to electrostatics, right? This is a slightly negative charge. This is a negative. This is a positive. But this is a very small atom. This is a much larger atom. So the distance between these two is much greater for essentially the same charge. So the closer you can get these two charges together, the stronger the bond. That's why HF is a weak acid and the rest of its halogens form strong acids. Okay, what if there's an oxygen involved? Well, what we find is that when we have oxygens around this atom, and we've got a hydrogen there attached to it, usually though the hydrogen's attached to one of the oxygens. There we go. So, again, bond polarity plays a role. This is a certain bond polarity here. And if you add another oxygen there, it makes it more polar because this oxygen is also pulling electron density away from the total. And if you put another one, it pulls it even further. And another one pulls it even further. So the more oxygens you have, the weaker the bond with the hydrogen. It makes a stronger acid. Now, perfect example. So we have these chlorate ion before we make an acid out of it, chlorate, chloride, hypochlorite, and perchlorate. So when we make an acid out of them, the strength of the acids increases that direction. And that's correlated to the number of oxygens. Perchloric acid is very strong acid. And I think we've got yeah. So these first four at the top of that list are like we have here. And notice that the K value for perchloric acid is very large, 10 to the 7th or greater. Chloric acid is about 1. And then we get weaker with chlorous acid, and then hypochlorous acid is the weakest at 10 to the minus 8th K. And you can get the same similar relationships for the other polyprotics or the other polyoxygen acids. Okay, how about comparing the electronegativity of X and the K value? Well, we're going to take, for example, we're going to try to compare apples and apples. So this hypochlorous acid, hyperbromous acid, hypoiodous acid, and then methanol. So we find that the more electronegative the halogen, the stronger the acid. Right? So the chlorine is more electronegative than the bromine, and stronger than the iodine, and that weakens the acid as you move down. And that's correlated directly with electronegativity. Okay, why not HOF? Why is an F in there? Well, it's a problem with decomposition. When you put HF in water, it immediately decomposes into HF and hydrogen peroxide. Now, there are some other compounds that when we put them in aqueous solution, they form either acid or base solutions. For instance, the acid oxides, they're called, are formed from non-metal oxides, sulfur dioxide, nitrogen dioxide, carbon dioxide. When you put those in solution, they always form acidic solutions. And the example at the bottom is one for sulfur dioxide, reacts with water and produces sulfurous acid. If you form an oxide from a metal, you get the exact opposite effect. So potassium oxide, calcium oxide, when you put those into solution, they form hydroxide compounds, just like this K2O down at the bottom. Okay, so those are the acid oxides, the basic oxides. And now we go to a concept called Lewis acid. We've talked about Arrhenius acids, bases. We talked about Lowry-Bronsted or Bronsted-Lowry acids. Now we're going to talk about Lewis acids and bases. Think of them as nested theories. The Arrhenius is at the center. It only covers a small number, by comparison, a small number of situations where you can identify acids and bases. Then around that takes it in plus more is Bronsted-Lowry. So we got Arrhenius here, and then we got Bronsted-Lowry, and now Lewis. Lewis takes them all in. Lewis changes the concept from acids being a proton donor to being electron acceptor. Electron pair acceptor. Look at it this way. There we go. So this would be an acid by Arrhenius definition. It has a hydrogen ion to be dissociated. It's also an acid by Bronsted and Lowry's definition because hydrogen is donated to water. Okay? Like that. But it's also an acid by Lewis definition because now it's an electron pair acceptor. The electron pair here goes over there. And now we have this proton available, and the electron pair acceptor is the acid. So an electron pair donor would be, by the other flip side of the coin, would be the base. Now, the advantage of this Lewis definition is that it works in non-aqueous solutions as well as aqueous solutions. And that is a real benefit to organic chemists. Many of the reactions that organic chemists are interested in have to take place in non-aqueous environments because water is a troubling reactant for some chemical reactions that they're studying. So they want to eliminate water from the reaction environment. And if they do that, then they can't use the Bronsted-Lowry definition or the Arrhenius definition anymore. But the Lewis definition allows them to think of chemical reactions in terms of acid-base, but without the nuisance of water. So in this example, the Lewis acid is the electron pair acceptor. This aluminum 3+ is the Lewis acid that accepts one of these pairs. Well, actually accepts, let's see. Well, let me think. 6 waters and only 1 aluminum. Well, I'm straining against a gnat. So let's just stick to the slide. Lewis acid is the electron pair acceptor. The Lewis base is water, which is the donator of the electron pair. And we have this polyatomic ion as a result. Okay, so these are all, this is just a table putting them all together. And they're nested. Right? Lewis takes in everybody. Bronsted-Lowry takes in itself plus Arrhenius, and Arrhenius is all by itself in the middle. Okay. So this is just a reminder, when you're analyzing an acid-base equilibrium problem, what are the major species? Does a reaction occur that can be assumed to go to completion? That's one step we haven't considered yet. Sometimes when you're conducting, and we're going to get to this in the next chapter, when you're investigating an equilibrium problem, it's very convenient, and often the only way to solve the problem is to let the reaction go all the way to completion. In other words, don't have the equilibrium to start with, go all the way to the end, and then set up the end products as your new reactants in an equilibrium environment. And that allows you to use the ICE table and solve the problem. So it's in 2 steps. You do a stoichiometry problem first, Then you take the results of the stoichiometry problem and set up an equilibrium problem and solve that one with your ice table. So that's where we're headed with the next chapter. The next chapter won't take as long. It's a shorter chapter. So let me see. I'm going to share. I think I've already got the set open. Here it is. And let's make a slideshow out of it. Can't reach it down there. Let me go up here. There we go. Now, in my textbook that I use at New River, these chapters are separated, and the second one is called acid-base equilibrium. But you'll notice from chapter 14 slides, we're already into equilibrium. So I think a better title for this would be, if anything, is acid-base buffers. That's where we're headed with chapter 15. The concept of buffering. All right, so let's hit the ground running. Okay, if you have an equilibrium situation, actually any kind, acid-base or not, and you do anything to disturb it, we already know that if you add a product, it'll shift toward the reactants. If you add a reactant, it'll shift toward the products, based on Le Chatelier's principle. So if we're trying to determine the pH of an equilibrium situation with a weak acid, then if there is a common ion already in solution, when we add the acid, that will affect the outcome. For instance, let's see, if we have, let's say hydrocyanic acid, right? We know it's going to do this thing, H plus, Cn minus, and it'll have a Ka for it. If you put it in water, then it's a simple calculation. Right, we know how to do that. But if you put it in, if you try to put more acid into a solution that already has cyanide ion there, then that will affect the outcome, because now your ice table is set up with a value here and a value here with a 0 there. So that you have to take that into account. And what that does is it tends to shift the equilibrium back that way anyway. And that will reduce the hydrogen ion concentration. So in general terms, if we have this type of situation where you already have some conjugate base, what we would call a common ion effect is at play. Then when we add some of this, it won't go quite as far to the right. And the pH will not be as low as you would expect it to be. Okay, so, oh, I didn't know this was coming. I just got lucky. Okay, so for this reaction, the addition of sodium cyanide will shift the equilibrium to the left, obviously, because of the addition of this common ion, the cyanide ion. So a solution of hydrocyanic acid and sodium cyanide is less acidic than the hydrocyanic acid alone in pure water. Right? That's just restating what I've told you already. Now, the reason we introduced the concept of common ion is this sets us up for a discussion of buffers. What is a buffer? Well, in chemistry, there are a whole host of different types of buffers. It depends on what you want to buffer. In general, what a buffer does is it resists any changes. So if we add more of this or if we add more of that, then the equilibrium will not shift very far. It'll stay very close to where it was. It won't be exactly the same, but it'll be close. And now for specifically acid-base buffers, we find that the pH will not change very much when we add acid or we add base to a buffer constructed out of a weak acid and its conjugate base. In order to have a buffer, you got to have both of them at the same time. You got to have some of this and you got to have some of that. For these types of problems, these are especially responsive to the use of that technique, stoichiometry first, followed by the equilibrium. I don't find these very useful, so I'm going to skip over this. Okay. So before we actually solve a buffer type problem, I want to discuss, historically speaking, work that was done by these two men, Henderson and Hasselbalch. They worked, Henderson came first, and he made a proposal. And then after he set up this reaction, there we go, and he said, if you want to solve for the hydrogen ion concentration or the pH, well, actually, he didn't know about pH at this time. Henderson came before Sorensen. So this is as far as Henderson could go. He said, if you want to find the hydrogen ion concentration, you need to know the acid dissociation constant for the weak acid. You also need to know, move that over the way. You also need to know the equilibrium concentration of the undissociated acid and the concentration of its conjugate base. If you know these three factors, you can calculate the pH. You can calculate the hydrogen ion concentration. Then Sorensen made his proposal, and Hasselbalch took that and ran with it from where Henderson left off. Okay, this was in 1908 was Henderson's publication. And then 1909, Sorensen proposed the pH system. And then in 1916, Hasselbalch made his transformation to Henderson's equation. And this is the way it ran. Okay, there you go. So we're down to Henderson here. So what if we take the negative log of both sides of the equation? We can do that. That's mathematically permitted. So here's what you come up with. Negative log of hydrogen ion concentration minus negative log of K minus the negative log or plus the negative log of this ratio. We know that this is pH and this is pKa, and it's more useful to leave this one as a log expression. Otherwise, we'd have to do a PHA and a PA minus, and that wouldn't be as useful. What we're interested in is what is this ratio at equilibrium? What is the ratio of, I erased it, the acid to its conjugate base? Okay. Notice that if these two, if this one is equal to that one, right? What do you get? You get 1. If they're actually equal, then that fraction is 1. So what's the log of 1? 0. That means if the acid to its conjugate base ratio concentration is equal, then the pH of the solution will be equal to the pKa of the acid. Now, Hasselbalch didn't like negatives any more than Sorensen did. So he said, okay, well, let's use this rule for logarithms, that if you have a quotient, then if you invert the quotient, you change the sign of the log. And that's what he did. He changed it to a positive by inverting the quotient. Okay, so this is the Henderson-Hasselbalch equation. pH equals pKa plus the log of the conjugate base concentration over the acid concentration at equilibrium. And this is an extremely useful equation. All right, so we're going to do an example where we calculate for an acid-base system. We're going to actually calculate it the old-fashioned way. And then we're going to show you how much easier it is and quicker to use Henderson-Hasselbalch. Oh, I just make a point that if the only thing that matters for this calculation is the ratio of conjugate base to acid. So if you have a very low concentration of acid and the low concentration of its conjugate base, you will get the same pH if the ratio is the same at higher concentrations. The only difference is what's the buffering capacity? And we haven't discussed that yet, but if you have higher concentration, then the buffer capacity is higher. It can withstand the addition of more acid or more base. Okay, so here we have an example. What's the pH of a buffer solution that is 0.45 molar acetic acid and 0.85 molar acetate? The Ka for acetic acid is 1.8 times 10 to the minus 5. Now that's an accepted value. Next week, we're going to actually calculate it from our titrations. Okay, well, all right. This one goes ahead and uses the Henderson-Hasselbalch equation, and we calculate that the pH should be 5.02 with these concentrations and this as your weak acid. Let's see, I was hoping we could. Okay, let's use this one. So if we have this generic acid, okay, and it's buffered, so we have some of this and we have some of that, right? The best, in fact, buffering occurs when this is exactly equal to that. I'll explain that later. So what would happen if we add acid? What does the acid do? Well, this is a weak acid here, so this is a strong base, which means it's looking for protons. If it's at equilibrium now, and you add acid to it, it's going to latch onto that proton and shift back this way. Okay? And when it does, it consumes these extra protons, not all of them, most of them, until equilibrium is reestablished. What if you add base, though? What happens to the base? Well, if you add base, and for simplicity's sake, let's say we add hydroxide as a base. The hydroxide is going to react with that proton. Because remember, where does hydroxide come from? Water dissociation. Water is a weak acid, so this is a very strong base. So it's looking for protons. So this one forms water, right? It removes that hydrogen ion from the product side. So which way is it going to shift? Le Chatelier says it's going to shift to the right and replace some of those hydrogens. So that's the concept behind buffering. No matter whether you add acid or base, it's going to hold the pH very close to where it was. Not exactly, right? Because you're dealing with an equilibrium system. So it's going to be a little bit off. You're going to add, if you add base, it's going to be slightly more basic than it was before. If you add acid, it'd be slightly more acidic than before, but it won't move much. As long as you have enough of these available in this equilibrium to consume any added acid or base. All right. So let's see. I'd already said that. I don't need to repeat that one. The pH is determined by the ratio of the concentrations of acid to conjugate base. And as long as the ratio remains relatively constant, the pH will remain constant. Here's a discussion of buffering capacity. So if you have a large amount of acid and conjugate base, then it can withstand the addition of more acid or more base before it's completely consumed, and then the equilibrium breaks down. And from that point on, any added acid or base will shift the pH either like that or like that. So the larger buffering capacity is preferable if all other factors are agreeable. And the reason I say that is a lot of these buffers are designed for living systems. And cells are very sensitive to particularly not just pH, but to ion concentration. It's the salt index of the solution. So if you make a buffer that's very, very high in the acid and the conjugate base, it may exceed the salt tolerance of the cell and destroy it, right? Purely based on osmotic changes. So you have to consider that also. Now, this quantifies the buffering capacity. It's given the Greek letter beta. So what it means is that this is the change in normality, due to the added acid or base. And normality, I think we discussed that. I don't remember if we discussed that or not. Normality is a concept. We know what molarity is. Right? So if we have 1 proton per molecule and say it's 1 molar, this will also be 1 normal because there's only 1 proton. But if we have a diprotic and it's 1 molar, this will be 2 normal because for every 1 you can produce 2 acids. Normality is very useful because it doesn't matter what the acid or base is. If you know the normality, then you can ignore the structure of the molecule. But I'm not going to make you responsible for this equation, right? We're not going to use it. It's just for information only. So for every change in normality, a change of normality will produce a certain change of pH. If the normality change by added acid or base is very large, but the pH change is very small, that means you have a very high buffering capacity. That's all that means. A large beta is preferable to a small beta, all other factors being equal. Okay, how do we choose a buffer? You usually know the pH where you want the buffer to settle. So if you're going to design a buffer to settle around a pH, you want that pH to be close to the pKa of the weak acid. Now I'm going to look to see. Okay, if we plot the curve, yeah, here we go. Plot the curve. We're looking for a couple of things. One is the equivalence point or the stoichiometric point. That's the point in the curve where the added acid and base are exactly equal. So, and that's what we're going to do next week. We're going to take our acid, acetic acid in a beaker, and we're going to slowly add incrementally sodium hydroxide solution, and we're going to count how much sodium hydroxide is added each time we measure the pH. And then we're going to plot it. So for our plot, let me try this. So we're going to have added base. And then this is the pH. So if we've got an acid to start with, it's going to be a low pH. Even if it's a weak acid, it's going to be a low pH. So for acetic acid, it's going to be down here around 3, between 3 and 4. Right? So we're going to start here. And then when we add base, the pH is going to start to rise. But as we do, we are producing conjugate base from the acid. In other words, if we used acetic acid, then we're going to set up an equilibrium like this. There. So as we add base, we're removing this proton, this hydrogen, from this equilibrium and producing more of this one. Okay. As we do, the pH rises to a certain point. And then when we get enough of this available, any added hydroxide is driven backwards to this one. Okay, so that consumes the hydroxide and stabilizes the pH. So eventually we end up with relatively flat area right in here for a while. And then as we add more base, we're consuming so much of this now that it cannot stabilize in an equilibrium situation. And then the pH starts to rise rapidly. And then it tails off at the top. This is called a sigmoid curve because it looks like an S. The stoichiometric point, or the equivalence point for this reaction, where the added base is equal, the moles of added base is equal to the moles of acid, is right here on the steepest part of this curve. This, if any of you have calculus, this is called the inflection point, where this curve is concave up, now it's concave down. The point where that takes place is right here. Okay, so this is going to be so many milliliters of base, right? Well, it just so happens that the middle of this flat part right here is exactly half of the equivalence volume right here. All right, so if we added 100 milliliters to get here, this would be 50 milliliters of added base. And at this point, we're halfway to equivalence. So that means that we've used up half of this and produced an equal amount of this, right? If that's the halfway point, then we still got half of that left and half of this produced. So that halfway point is, this is equal to that. Right? So here's the Henderson-Hasselbalch plus log of conjugate base over the acid, C, O2, here we go. And if these two are equal to each other, this term right here, right, that's one, this term drops out. So at that point, the pH is equal to the pKa right here. So you just walk your way over here. That pH is the pKa. Okay? That's what we're going to do next week. We're going to do the titration, draw it out, find the halfway point, find out the pKa of acetic acid, and then pKa is equal to the negative log of the Ka. Right? So we just say 10 to the negative pKa is equal to the Ka. And there's the answer right there. That's what we're shooting at right there. It should be close to, what was it, 1.8 times 10 to the minus 5, something like that. Okay, so that's what this is all saying. Now you can do the titration just as easily if you have a base in your beaker and you're adding acid to it. In that case, it would start from up here and it would gradually drop down and then it would flatten out. And then it would go like that. So the halfway point there would give you the pKb of that base. Okay. So when we do a titration, which is what we've been doing here, you're adding typically an acid-base titration is used to determine the exact concentration of acid or base in the unknown. When you add a known amount of a known concentration of the opposite, either the acid or the base, and then you can calculate the concentration of your unknown. That's typically how we use a titration. But in this case, we're doing a titration to find out that value. But we could just as easily, determine what's the concentration of the acid. We already know what it is, so that's a moot point. All right. So when we have a weak acid, strong base titration like this, we typically, if we want to find out what the pH is, we work it as a stoichiometric problem first. And we assume that the reaction goes to completion. And then that's where we start and work our way back to with an equilibrium problem. So here's an example. All right, we have, I think I need another marker. Let's try this one. So if we have a solution made by mixing 0.1 mole of HCN and 0.04 moles, notice that's not molarity, that's moles, of sodium hydroxide in 1 liter of aqueous solution, we're looking for the pH, the final pH of the solution. So what are the major species? Well, when you start, HCN, sodium hydroxide, and water, right? HCN is a weak acid, so major species is going to be undissociated. Sodium hydroxide goes straight into solution, separates into sodium and hydroxide ions, and then you've always got water. So what are the reactions? Well, you got water, you got HCN and water, you got HCN and hydroxyl, you got sodium and hydroxyls, and you got sodium and water. And obviously those last two are going out, right? So here's what we do first. We use this number 3 equation and take that one to completion. Right? We're going to take this one to completion first, because that's the reaction where you're adding hydroxyls to the HCN and consuming them. Right? So then we, at this point, we have major species are HCN, CN minus water and sodium. Right? Sodium doesn't matter. And, well, it's not going to let me go any further. All right. So here's another one. If you don't get whiplash from this, what's the pH of a solution made by mixing 0.2 moles of acetic acid with 0.03 moles of sodium hydroxide in 1 liter of aqueous solution? Okay, so the major species are those, right, at the beginning. Those are our possible reactions, and we throw these out because they don't make any sense at all. And the stoichiometric reaction is number 3. We do that one first, right? Because it's the one that's going to, let's see, here we go. the strong base hydroxyl will react with the strongest proton donor. So we got a strong proton donor, and we have a hydroxyl here, and this is our stoichiometric reaction. We do that one first. Right? So if we're going to let it go to completion, that means all of the hydroxyls are used up, and they consume 1-to-1 ratio. They consume this much. And remember, we've calculated the molarity before to do this, right? It was all in 1 liter, so it's just the moles divided by 1. So what do we have left over? Well, now at equilibrium, at this point, which is actually stoichiometry, at this point we have 0.17 molar of acetic acid left, and we have 0.03 molar of acetate ions produced. Okay? Now the controlling reaction is the acetic acid dissociating into hydrogen ions and acetate ions. And our starting position now is 0.17 because we've consumed some of them and produced some of these. Now this is our new starting point. And we run our calculation, right? We have the Ka here. 1.8 times 10 to the minus 5 is equal to this value. And we're saying that these X's are so small that they're insignificant. So now we find that the pH is 3.99 based on this. Okay. Guess what? Once we determine 0.17 and 0.03 and the X's are insignificant, we can plug those values into Henderson-Hasselbalch and get the same value, 3.99. So that's the quick way. Here's another one. Let's see. What's the pH of 100 milliliter solution of 0.1 molar acetic acid, which has a Ka value of 1.8? All right. 2.87? Okay. Actually, the volume doesn't matter. Only the concentration matters. Come on. There we go. So what's the pH of 100 milliliters of a 0.1 molar acetic acid with this Ka if you add 50 milliliters of 0.1 molar sodium hydroxide? Now we've gone from the acid into the titration curve where we've added some sodium hydroxide. All right, so what we need now is to let that reaction go to completion first. Now, how did we get these initial values, 0.0667 molar and 0.033 molar? Well, how many moles do you have here? Acetic acid plus hydroxyls yields acetate and water. I don't like that color. Let me try a darker one. Okay, so we started off with 100 milliliters of 0.1 molar acetic acid, 100 milliliters of 0.1 molar, right? You know how to get the number of moles there? Well, actually millimoles in this case. This is 10 millimoles. And we're starting here with 50 milliliters of 0.1, there it is, 0.1 molar of that one. So that would be 5 millimoles. Okay, so what's the concentration? Well, if you divide millimoles by milliliters, you get the concentration. But now we don't just have 100 milliliters, we have 150 milliliters. And 150 milliliters. So this is equal to 0.00667, right? Yeah. And this is equal to 0.0333. No, my mistake. Too many zeros. I thought that looked funny. This is a 0. This is a 0. 0.0667 molar. So this is our starting point for the stoichiometry. Then we're going to use up all of this and some of that, and our new equilibrium starting positions for the return reaction is 0.0334 molar acetic acid and 0.0333 molar acetate. Okay, so all we have to do is plug them into the equilibrium expression, Henderson-Hasselbalch, and we get a pH of 4.74. So that's the pH that we should arrive at if we add 50 milliliters of 0.1 molar sodium hydroxide to 100 milliliters of 0.1 molar acetic acid. Okay, well, you can do this with base also, but it takes a little bit of work because the Henderson-Hasselbalch equation is based upon the Ka. All right, so it just takes a little bit of extra effort. There's our stoichiometry, right? We got ammonia plus water yields this. Let's see, 100 milliliters of 0.1 molar and 50 milliliters of ammonium chloride. Okay, so what we're doing now is we're building the buffer from the start. Notice that this is the base, this is the conjugate acid. We're adding this much base and we're adding this much conjugate acid. So what is the final concentration? Well, the equilibrium expression now will be set up as starting points will be 0.0667 minus X, and we did the same type of calculation as before because now we have a new volume, right? So we have to calculate the number of moles of each and divide it by the new volume. That's why these values don't exactly equal the ones that were given here. Okay. And then okay. Oh, we were already given the Kb value, weren't we? Yeah, we were given Kb already. This is a Kb reaction, ammonia plus water. We can drop the X's and solve for the 1X, and the pOH is 4.44 and the pH is 9.56. And we're just telling you that it satisfies the 5% rule, so we don't have to go through the calculation. This is the long way around. Now, suppose we want to use Henderson-Hasselbalch. So we have this equilibrium position here, but we need a Ka in order to use Henderson-Hasselbalch. So we take the Kb of this reaction and calculate the Ka, and the Ka is 9.25, right? The Kb was, excuse me, the Kb is 1.8 times 10 to the minus 5, so the Ka is that divided into 10 to the minus 14 is 5.56. So the pKa, that's what we're calculating here, because that goes into the Henderson-Hasselbalch equation. Now we can put the pKa here, and we can put the conjugate base in the numerator. So it's this value. That's important. Conjugate base in the numerator. This is the acid. That's the conjugate base. And we come out with 9.56, which is the same as we got before. We just had to calculate the Ka in order to use Henderson-Hasselbalch. Okay. So what do we got here? Calculate the pH of a solution made by mixing 1 liter of a 0.5 molar solution of ammonia with which has a Kb value of 1.8 times 10 to the minus 5 and 0.5 liters of 0.1 molar ammonium chloride solution, and then add 0.1 moles of HCl gas. All right. So when we first start out, we have 0.5 moles of ammonia and 0.1 mole of ammonium ion. Okay, in order to make this simpler calculation, we're going to go with absolute amounts first. So that's why we don't have concentration here. We're working with absolute amounts. So this is what we have to start with, absolute amounts of ammonia and ammonium. Then we're going to add HCl. Okay, so we're starting off with 0.5 moles here, and we're adding 0.1 mole here. And we're starting off with 0.1 mole of ammonium ion. Okay, when we do that, this reaction gives us more ammonium, right? We're going to consume all of that and make more ammonium. Now we have 0.4 mole left of ammonia and 0.2 moles of ammonium. This is the stoichiometry. Now we're going to have to calculate the concentration of the new values. 0.4 divided by 1.5 liters because we added some volume. So this is our starting point with the base and the acid. Henderson-Hasselbalch, we need that Ka, and then we can plug in the values that we determined. And our new pH is 9.55. Okay. Here, this example is one we want to calculate the pH of the solution at the equivalence point when 100 milliliters of 0.1 molar acetic acid with a Ka of 1.8 times 10 to the minus 5 is titrated with 0.1 molar sodium hydroxide. Well, if it's at the equivalence point, then we have to add exactly the same number of moles of base as we have acid. Right? That's what this explanation in green means. So when we go to completion, the concentration of both before the reaction is 0.05 molar because we have a new volume, right? 100 milliliters. And we have to add, since they're the same concentration, we have to add exactly the same volume of base. So now we calculate the new concentrations. And the initial concentration now is 0.05 molar for the acid, 0.05 molar for the base. And both of them are consumed, right? We're at the equivalence point, so there's nothing left. Now we have the acetate ion at 0.05 molar. Now the dominant reaction is, what does that acetate ion do? The acetate now reacts with water. Right, so we have 0.05 minus X here and X here and X here. So we need a Kb for this reaction. And if we have the Kb, then we can set up our equilibrium expression and solve for X, which was now be OH, take the negative log of it, subtract that from 14, and our pH is 8.72. So this titration puts us close to 9. That's why we use phenolphthalein. And that's going to be the next discussion, I think. There's the titration curve, and the equivalence point is close to 9. Okay, I was jumping ahead. When you do titrations with a base against a weak acid, you'll get this similar sigmoid curve. This one right here is, yes, this is a Ka of 10 to the minus 4, which is close to acetic acid. Acetic acid would be right in the middle. So it's going to come up in this range, and then it's going to go over here. And then if you have a weaker acid, it's going to have a starting point of higher pH because it is a weaker acid. but it's going to have a similar shape to it. All right, and you can go backwards, right? You can start off with a base and titrate with an acid. Okay, so indicators. You choose, first of all, an indicator is a weak acid. So if we have a weak acid, we're going to use this expression, HIN. So there's the indicator with its proton. And it undergoes an equilibrium that separates the proton from the indicator part of the molecule. Okay? And this has its own K value. There's some kind of K here for that one. All right? So, let me continue with the slide. It'll help. We pick our indicator so that we can tell the difference between one side or the other. So if we're titrating with base, right, it's picking up this part of the molecule. It's picking up these hydrogen ions and shifting back toward that. So what we want is a color difference between this side and that side. For phenolphthalein, this side will be colorless. Okay, and this side will be pink. Okay, so the pKa for phenolphthalein is calculated there for you at 9.4. So at a place where these are equal, that's where the pH is equal to 9.4, right? Just like any other acid-base, a weak acid equilibrium. If these are equal, then the pH is 9.4. The problem is physiology. Our eyes can only detect a certain amount of difference between the two. And the fact of the matter is the difference has to be a 10 to 1. So you got to have 10 times as much of this as that to see it colorless, or 10 times as much of this as that to see it pink. So there's a difference between the two in concentration of actually 100, which is a power of 2. So a pH change, the pH is plus or minus 1. 1 above, 1 below. So that means that the pH that we want, the pH that will give us a distinct color change is plus or minus this value. Because if they're equal, then we want to shift them this way or that way. So this one, plus or minus 1, will give us the pH range, roughly speaking. So this would be 8.4 to 10.4. Actually, it's a little narrower than that, but this is for discussion purposes. So the main point here is that when you know the pH at equivalence, and we determined that earlier, right, for this titration here, for acetic acid, when we're titrating acetic acid, the pH is going to be 8.72. Right? So 8.72 is right here. It's in the middle of the range. So phenolphthalein would be a good choice. All right. So here's a discussion of the difference, the 10 to 1 ratio that's required in order to produce a recognizable change in color from colorless to pink or pink to colorless. And you can use that argument for any one of the other indicators that we have. And I think that's on the next slide. Here we go. It's kind of hard to see, but you'll see a list of the pH indicators over here and their usable range of color change and along in here. And these ranges are all related to the pKa of the indicator. Let's see, phenolphthalein is right down in here, right here. Right. So between, right in this range, gives you the change. That's why when we, during first semester, when we were doing titrations with our phenolphthalein indicator, you wanted to titrate until you got the solution to turn pink, just pink and stay pink, but not more, because you want to be very close to the center of that color change range. Because the equivalence point is 8.72. Right, so you want to be right in the middle. Actually, the sooner the better. Right, when it just barely turns pink, that will give you the best results. All right, I think that's it. I think this is the last slide. Yep. So we're done. All right. So next week, let me see. Let me mark this off on my calendar. We did that. We did that. We did that. So next week, we'll do a review on chapters 14 and 15 in the first part of the class. And then the second part, we'll do this titration to determine the Ka for acetic acid. This one should be fairly easy to understand. I mean, if once you got the graph up there and you see the curve and you know exactly where to go to find the pKa, it's a piece of cake.